This is the Math 2 lesson summary video for the lesson entitled The Wow Factor. In Lesson 7, The Wow Factor, the purpose of this lesson is to extend our understanding of how to factor a quadratic function when our a value is not equal to 1, as in the previous lesson. In the previous lesson, we saw how we can use rectangles to represent the area of orders received by Optima's quilt shop. We summarized the lesson by determining that we can factor a quadratic when a is equal to 1 by finding two numbers that multiply to c and add to the b value. In this lesson, we are going to expand our understanding of how to factor when our a value is not 1 for the quadratic function. We are asked to represent the first order that contains a block that was exactly twice as big as the rectangular block that has a side that is 1 inch longer than the basic size x, and one side is 3 inches longer than a basic size. We would draw this as the diagram shown. This represents our x plus 3 times an x plus 1 side length. Since we have two of the same blocks next to each other, we can represent this as 2 times an x plus 3 times an x plus 1 area. Another way to write that is if we distribute our values in the parentheses, we could also write this area as 2 times the quantity x squared plus 4x plus 3. If we distribute the 2 to each term in the trinomial, a third way we can write this is 2x squared plus 8x plus 6. We are then asked in number 2 to unscramble the order. This is the order Optima's shop received. So the pieces would provide us with an area. If we look at this order and we just add up all of our x squareds, we have 3 x squareds, we have 15 rectangles, and we have 18 constants. One way to represent this area would be 3x squared plus 15x plus 18. If we are drawing a diagram like we've done in the previous lesson, this would be an x plus 3 side length and an x plus 2 side length. We are multiplying those to find the area of this shape here, and we have 3 of those. So another equivalent way to write this area would be 3 times x plus 3 times a side length of x plus 2. And a third way, of course, would be to redistribute, which we've already done over here. So we have several ways that we can write the area of these shapes. We are asked to find equivalent expressions for the quadratic functions in number 4. If you look at 4a, we are given the area of 5x squared plus 10x. We know that this means that we need 5 shapes of equal area. If we divide both of these by 5, we will be left with x squared plus 2x. If we take a look at our diagram, we know then we should have an x squared area plus an x plus 2. If we take out the x along with the 5, we would get a side length of x plus 2. If you look at the diagram drawn, you can see that this is an x by x area, or x squared, and we have x plus 2. If we count how many we have 1, 2, 3, 4, and 5 of these x by x plus 2 rectangles. Therefore, we can say that an equivalent expression would be 5x times the quantity x plus 2. In 4b, we are given the order area of 3x squared plus 21x plus 36. We know that this contains 3 of the same rectangle areas. If I divide all of my terms by 3, I'll be left with x squared plus 7x plus 12. To find an equivalent expression, we know from the previous lesson that this would give us a side length of x plus 4 by x plus 3. Recall in the previous lesson that if we find two numbers that multiply to the c value, that should also add to the b value. Therefore, we know an equivalent expression here could be 3 times the quantity x plus 4 times the quantity x plus 3. If I look at my diagram, I see that this is an x by x square, and I have plus 3 as a side length and plus 4. Therefore, I know that this area of this rectangle is an x plus 4 by an x plus 3 area. And how many of those do I have? I have 3. 1, 2, 3. Therefore, this expression is accurate. With our partial orders in number 6, we are first given that one side length of the rectangular quilt needs to be x plus 3. And our total area for the order needs to be 2x squared plus 7x plus 3. If we examine a diagram of the area, the other side length would need to be 2x plus 1. This is my x plus 3 side length, and this would be my x plus 1, or 2x plus 1 side length. Therefore, another way to write this would be the quantity 2x plus 1 times the quantity x plus 3. For b, the side length we are given is x plus 1. And the other side length would need to be 5x plus 3. There's an x plus 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 a 3. Therefore, this equivalent expression would be 5x plus 3 times the quantity x plus 1. We are asked in number 7 to then conclude some patterns that we've noticed while trying to come up with equivalent expressions for each of these quadratic functions in standard form. We notice that the first term in the standard form trinomial will be the product of the first two terms of each factor. For example, if we look back at b above, 5x squared plus 8x plus 3. I know in my two factors that my first two factors should multiply to 5x squared. Therefore, 5x by x will give us 5x squared. We also noticed that the last two terms multiplied together, in this case the 3 times the 1, will always provide us with the c value in the original function. So in this case, we did 5x plus 3 times the quantity x plus 1. That will always work. If we wanted to check our answer, we know mathematically that we can multiply and redistribute. We would get 5x squared plus 5x plus 3x plus 3. When we combine our like terms, that would yield us 5x squared plus 8x plus 3, which is exactly what we started with. Therefore, we can always check that our expressions are equivalent. Examining the trinomials in number 12, we used our patterns that we noticed in number 7 in order to write these as two factors. We first looked to find factors of 6x squared. We know 6x times x will give us 6x squared. We also know that 2x times 3x will also give us 6x squared. We need to try our two factors in each of the two spots in our binomials. The next thing we noticed in the last example, a pattern, was that our last two values always multiply to the C value. Our only factors are 2, and 1. What we will need to do is plug these values in so that we can see which ones work. If we plug in 3x plus 2 and 2x plus 1, we want to redistribute to make sure it's equivalent to our original function. 3x times 2x is 6x squared. 3x times 1 is 3x. 2 times 2x is 4x. And 2 times 1 is 2. When we combine our like terms, we see that 6x squared plus 7x plus 2 is indeed our original function. Therefore, we have factored this correctly and written it as an equivalent form. We were asked to write a recipe for how to factor trinomials where a was not 1. We wrote down some steps. In the first step, you want to check to see if the terms have a common factor. For example, think about our diagrams. If there were more than one of the same rectangle, we had to draw it more than once. So the first step will be to take out that common factor. You will divide that common factor by all of the terms. If I look back at an example we did earlier, that means you would divide this by 3. You would have 3 equal rectangles of x squared plus 7x plus 12 area. Consider the expression that remains. We know that we can factor this further. Keep your common factor on the outside, and you're going to go back to factoring, finding two numbers that multiply to C and add to B. In this case, recall that would be x plus 4 times the quantity x plus 3. Make sure that you check your signs, which we went over in the previous lesson. Always check your factoring to be sure that the middle terms turn out right. Rearrange your numbers if necessary. If you need more help on the Ready, Set, Go homework for this task, please check the Canvas Student Support site.